Yes, we shall begin with the next part of this topic is known as the oxidation states, which are also very easy to study because some part of this that we have already studied in the last year. So oxidation states. Now, how can we define oxidation states? Oxidation state can be defined as it is a numerical value. It is a numerical value. What is the numerical value? Either one digit 1, 2, 3, 4, and so on. It is a numerical value with sign of charge. We know the charge may be positive or the charge may be negative. So oxidation state can be defined as it is a numerical value with sign of charge which an atom appears to possess in an element. For example, we always write barium as +2. So here plus is a sign and numerical value is a 2. So the numerical value is 2. For phosphate ion, we can write this is a PO4 3-. So there is a negative charge and numerical value is 3. So oxidation state can be defined as the numerical value with sign of charge which an atom appears to possess in an element. Now the question arises that there are again differences. How can we write the oxidation state? Suppose if I write oxidation, the word oxidation state, or if I write oxidation number, then oxidation state can be written in Roman letter 1, 2, 3, 4, like that. And if we refer as it is oxidation number, then we can write simply number 1, 2, 3, 4, like this. So suppose for example, if we want to write the copper plus oxidation state, then we can also we can write like this, or Fe+3. This is Fe+3. Same can be written in the form of oxidation number like this. So don't make confusion between the oxidation state and the oxidation number. Oxidation number means we have to write the numbers, and state can be defined, represented with the help of a numerical, Roman numeral. Now, again, we can write for all these elements the different oxidation states. So again, I shall refer the same electronic configuration here. And I shall prepare one column for which we can write this as like this: the oxidation states and outer electronic configuration of M+2. That means metal in +2 oxidation state, metal in +3 oxidation state, and metal in +4 oxidation state. All these are the metallic elements. Hence, I have used the word M+2, +3, and +4. In the beginning, we have seen that these elements also show a variable oxidation states or variable valency. So more than 2 valencies, if an element that shows, it is known as a variable valency. Now we have to show the different oxidation states for all these elements. So in the beginning that I have shown you that all these elements are placed in group 3rd-B of the periodic table. See here, all these elements are in group 3rd-B group of the periodic table. So in the group in which it is placed, that group valency is attributed. Say for example, in group first A, first element is hydrogen, so group valency is +1. Then lithium +1, sodium +1, potassium +1. So H, Li, Na, K, Rb, Cs, Fr, all these are first A group elements. They show the +4 oxidation state or +1 oxidation number on account of the group valency. Second A group of the periodic table, which starts with the beryllium +2, then magnesium +2, calcium +2. So +2 is again on account of the group valency. Similarly, if all the lanthanide elements are in group 3rd B of the periodic table, we have to write only +3 oxidation state for all these elements. So you have to listen and see this table form very carefully, because later on there will be some complications are there. So I shall write lanthanum +3 on account of the group valency, Ce +3, Pr +3, Nd +3, Pm +3, Sm +3, Eu +3, Gd +3, Tb +3, Dy +3, Ho +3, Er +3, Pm +3, Yb +3, and Lu +3. So I have written the +3 oxidation state for all these elements. So a MCQ based question may be asked. The principal oxidation state, or major oxidation state, or common oxidation state, which is shown by all the lanthanide elements, is +3 on account of the group valency. जो एलिमेंट ज्या ग्रुप मध्ये असते त्या ग्रुपची व्हॅलेन्सी त्या एलिमेंटला असते हे आपण शिकलेलो आहोत. सो these elements, they do display +3 valency on account of these elements belong to 3rd B group, the group of the periodic table, and hence they do display +3 valency. Now +2 oxidation state, that is shown by +2, that is a minimum oxidation state shown by the element neodymium Nd +2, then Sm +2, then Eu +2. These are 3 elements, and Tm +2 and Yb +2. So these are the 5 members. They do display a minimum oxidation state in addition to +3. So ytterbium +2 +3, thulium +2 +3, europium +2 +3, samarium +2 +3. All other elements, they only show +3 oxidation state. Now come to highest oxidation state. Here the +4 oxidation state is shown by cerium, then praseodymium, and neodymium. So these are the 3 members. They also show the +4 as the highest oxidation state, and atom number 66, terbium and dysprosium, they also show the +4 oxidation states. So these are the 5 members. They do display +2 oxidation state, and these are the 5 members. They show highest oxidation state. So here, if you look for neodymium, so neodymium can show 3 oxidation state, +2, +3, and +4. Samarium shows only 2 oxidation state. Again, terbium 2 oxidation states. So like this, we have arrived at all the oxidation states for these members. So +3 is a common or major oxidation state or principal oxidation state. Now we have to arrive at the outer electronic configuration. How to write the outer electronic configuration of all these ions? Just see here. Now here, neodymium, as we know, it is having the configuration as, yes, look at this electronic configuration, neodymium. If we keep this parallel, so neodymium is having the electronic configuration as a xenon 4f4 5d0 and 6s2. So the orbital which is filled early, those electrons should be removed early, and later on other electrons are to be removed so as to arrive at the plus oxidation state. So if these two electrons are lost by neodymium, then the configuration becomes 4f4. So here we can write only f4. It is not necessary to write 4f4 because all lanthanides they belong to 4f series, hence it is, we can write only f4. Now similarly, how can we write the electronic configuration for the outermost electronic configuration for samarium? See, this is electronic configuration for samarium, that is a 4f6 and 6d0, sorry, 5d0, 6s2. To show plus 2 oxidation state, it should lose 2 electrons. So only 6 electrons are left with samarium. So we can write this is f6. Now come to europium. Europium 4f7, 5d0, 6s2. To show plus 2 oxidation state, it should lose 2 electrons. So configurations become 4f7 or f7. For thulium, see, this is an electronic configuration of thulium. Have you seen this? Yes. This is electronic configuration of thulium and ytterbium. Thulium is having electronic configuration 4f13, 5d0, 6s2. To show plus 2 oxidation state, it should lose 2 electrons. So configuration becomes 4f13. And for ytterbium, after loss of these 2 electrons, it becomes 4f14. So these elements are having, or these oxidation states, for neodymium, samarium, europium, thulium, and ytterbium, they show these F4, F6, F7, F13, and F14 configuration. Now, here, come to this plus 4 oxidation states. Now, see this. For cerium, the electronic configuration is 4f2, 6s2. 5d0. So to show plus 4 oxidation state, it should lose all the 4 electrons. So 2 electrons from 6s and 2 electrons from 4f. So it becomes f0. For praseodymium, this is the electronic configuration 4f3, 6s2. So it becomes 2 electrons should be lost from this. So it becomes f1. And for neodymium plus 4, again, sorry, here this is a loss of these 2 electrons and loss of 2 electrons, it becomes 4f1 and here 4f2. So this is how we, if we go on removing the electron, then for terbium, it becomes, for terbium 4f4, that means it becomes f7 and this is f8 for dysprosium. So by removal of 1 electrons or 2 or 3 or 4 electrons depending upon the oxidation states which are shown by either of these elements. So this is how we have arrived at all these different electronic configuration of the corresponding oxidation states. Now, if we want to write the electronic configuration for lanthanum plus 3 ion, then look at this electronic configuration again. See this electronic configuration of lanthanum. Lanthanum having electronic configuration as F0, D1, 6s2. To show plus 3 oxidation state, these 2 electrons and 1 electron lost, that means becomes F0. For to show plus 3 oxidation state for cerium, it should lose 2 electrons from 6s, and here there are 2 electrons are there. So 1 electron should be lost, it becomes F2. So if we go on removing 3 electrons from the electron configuration of these corresponding ions, then we can easily write this as a F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, then F13, 14 like this. So here, this is how we can write the electronic configuration for here. There should be F1, 2, 3, 4, and for lutetium we have to arrive at F14. Now, suppose during your exam, because your exams are online MCQ based exams, so I am repeatedly telling you that you have to by heart the series. Once you by heart the series, then you will arrive at the electronic configuration for all these elements. Now, suppose during last year semester second examination, they have given the ion like this, Nd equals 4, and they have given 4 different options that neodymium plus 4 shows the electronic configuration, and they have given different options. So here amongst these options, just now we have seen that F4 is the correct answer for neodymium plus 4, or they will give you the outermost electronic configuration and you have to arrive at the corresponding electronic configuration, or they may give one of the oxidation state from +3 or one of the oxidation state from +4 also. You have to arrive at the oxidation state. So if it is given dysprosium +4, then you should write dysprosium +4 means DF8 configuration. So I am telling you again, once again, that you must by heart the series, including the corresponding correct electronic configuration. Now we have completed the oxidation state. Now again, how, in what basis the electronic configuration that depends? The electronic configuration that depends upon the extra stability or extra stable oxidation states. Which are the extra stable oxidation states? Those oxidation states where F0, F7 or F14 configurations are observed, all those oxidation states are extra stable. For example, look at this electronic configuration. Lanthanum +3 is extra stable because of F0 configuration. Then europium +3 extra stable because of F7 configuration. Then here lutetium +3 extra stable because of F14. Again, amongst lower oxidation state, ytterbium +2, it is also extra stable because of F14 configuration. Then europium +2, again extra stable. So here, let me confirm. Yes, it is europium +2, it is also extra stable because of F7 configuration. Now, from +4 oxidation state, terbium +4, again F7 configuration. So these are the configurations which are either completely empty, half filled or completely filled. They offer extra stability. But here we have also shown some other oxidation states. For example, ytterbium +3, which is having F13 configuration. Even though it is stable because it is short of only one electron, but their stability depends upon some other thermodynamic and kinetic aspects. So this is how we have to arrive at the different oxidation states. So here today, we have completed the electronic configurations for all these 15 elements comprising from lanthanum atom number 57 to lutetium atom number 71. While looking at the electronic configuration, we have shown that F7, that is atom number 63, europium, and F14, that is atom number 70, ytterbium. These are the two elements, or these are the two members. They do display the extra stable electronic configuration. The same is true for while writing the oxidation states. So we have written different oxidation states for all these members, and we have shown that their stability that wholly depends upon the acquiring F0, F7 or F14 configurations respectively. There are certain other elements which also display other configuration, for example, F1, F2, F13, F12. These are also stable, but these are not extra stable. Their stability can be determined by using some other kinetic and thermodynamic aspects. So this is how today we have completed the two aspects from this topic. In due course of time, I shall begin with the magnetic properties of all these elements and the colored ions. To study these aspects, you should remember the entire series with the corresponding correct electronic configuration. So I want to stop here because very less time is left. So take care of yourself, stay at home.